Hello everyone, let's start a new lecture series, and the name of the chapter is Chemical Equilibrium, a Thermodynamic Approach. It may also be regarded as the continuation of the chapter Application of Thermodynamics. In this context, let's start with the conditions for equilibrium. You know from your previous knowledge that what are about the conditions for equilibrium and spontaneity. So the thermodynamic parameters at equilibrium follow the conditions. The value of delta G should be 0, delta A 0, delta H 0, delta U 0 and delta S 0, and their corresponding positions are at the equilibrium point. All the energy terms G, A, H and U are minimum, while this energy by temperature term, that means entropy, is actually remaining at the maxima. Okay, so these are the conditions, and also there are some other suffixes such as the free energy change should be taking place at constant pressure and temperature, and work function at constant volume and temperature, enthalpy at constant pressure and entropy, while internal energy at constant volume and entropy, and in case of entropy at constant internal energy and constant volume. That means isodynamic and isochoric. This one isochoric and isoentropic. This one isobaric and isoentropic. This one isochoric and isothermal. This one isobaric and isothermal. Okay, so now let me start the new thing, which is the derivation of the equilibrium constant. Okay, and in this regard we have to take a generalized chemical equation, chemical reaction taking place between A moles of A, B moles of B, C moles of C, and the products are P moles of P, Q moles of Q, R moles of R. Here number of moles are in the small letters and the species are written in the capital letters. Okay, and this reaction has attained equilibrium at constant temperature, and for this reaction the Gibbs free energy is taken to be G. Okay, so if G is the Gibbs free energy, then if the reactants, that means A, B and C or etc., they diminish by minute amounts by the proportion of delta X. That means if A is present in 1 mole, that means delta X. If A was present by 2 moles, then it is 2 into delta X. If A is present by 3 moles, then it is 3 into delta X. So delta X is the proportionality. So from that perspective we can write that amount of A is slightly decreasing. Okay, how much amount of is decreased? Amount is small letter a into delta X. So these are written here. If the reactants diminish means they decrease by minute amounts, that means very small amounts, say A into delta X, B into delta X and C into delta X. So simultaneously what would happen? The amount of the products would also increase. So here it is written, and consequently the products are raised by minute amount. Okay, say P into delta X, that means delta X is the proportionality. Okay, and at this proportion all the reactants are decreasing and products are increasing, and their respective number of moles are multiplied with delta X. Okay, so P into delta X, C into delta X, R into delta X, these are the amounts they are increasing. Then from Gibbs-Duhem relationship, you know this Gibbs-Duhem relationship in the chapter Application of Thermodynamics in the previous lectures. So this relationship, the change in chemical potential of the system may be written as. So we would use the Gibbs-Duhem relationship, and now we shall write here the change in chemical potential of the system. So what is the change in chemical potential of the system? Now it is delta G equals to sum over mu dN. So what is mu? Mu is the chemical potential of the individual components. And what is dN? dN is the change in amount of the component. Component means if it is A, then it is A component. If it is B, it is B component. So actually this is actually delta X. If it is A, it is A into delta x. If it is B, it is B into delta x. Okay, so this way they can be written. And mu, in case of A, it is mu A. In case of B, it is mu B. This way. Okay, so what is the value of delta G? The free energy change. Actually, it is the free energy of the products minus the free energy of the reactants. Okay, free energy means chemical potential into number of moles. Okay, so chemical potential into number of moles of the products minus chemical potential into number of moles of the reactants. That means, and here summation sign is given. That means the overall change of the reactants. Here also the overall change of the products. Now let us put the respective values, and the respective values of for the products are, here instead of mu we shall write here mu p, and instead of dn we shall write here p into delta x. Similarly for q we have to write mu q into small q into delta x, and so on. Similarly for the reactants we can write chemical potential of A into number of moles of A into delta x, isn't it? And for B, mu B small b into delta x, and so on. Now at equilibrium, what is the condition of equilibrium? As we have seen in the last slide, that the condition of equilibrium is delta G equals to 0. Okay, yeah, there are some conditions that the temperature and pressure should be kept constant. Okay, no problem. It is, you have to keep it in your mind that the temperature and pressure are constants. You are not writing them here, but you are keeping in your mind that the temperature and pressure are constant. So delta G at constant temperature and pressure are 0. Okay, let's keep the temperature and pressure of the system constant. That means the reaction is taking place isothermally and isobarically. Okay, so if delta G is 0, then this is 0. That means this part within the parenthesis should be equal to this part within the another parenthesis. Okay, that means these two are equal to each other. So we have written here mu p into small p delta x, mu q into small q delta x, and so on, equals to mu a small a delta x plus mu b small b delta x, and so on. Now delta x can be taken as common in the left hand side, as well as the same can be done in the right hand side, and this delta x would cancel another delta x in the left hand side. So only the terms which are left behind in this equation are the everything except delta x. So the left hand side would become mu p into small p plus mu q into small q, and so on. And in the right hand side, what is left? Now mu a into small a plus mu b into small b, and so on. Okay. Now we know the expression of chemical potential mu as mu 0 plus RT ln A, where A is the activity of the species and mu 0 is the what? Mu 0 is the standard chemical potential of that species, and since the temperature is kept constant, so that constant temperature is T. So with respect to mu 0 T and A, mu can also be expressed as mu 0 plus RT ln A, and this relationship can be applied for all the species in the previous equation. In the previous equation, what was here? Here was mu P. Okay, so instead of mu P, you can write mu 0 P plus RT ln AP. That means mu 0 P is the standard chemical potential of P species, whereas AP is the activity of the P species, and small p is the number of moles of the P species. Similarly, the same thing applies for Q and R, and in the right hand side the same thing applies for A, B, C, and so on. Now this part of this relationship is the variable part, while this part is the constant part. Okay, so we have separated these constant parts with the variable parts, like the next line, where it is written that the variable parts are taken in the left hand side while the constant parts are taken in the right hand side. Okay, so these are the variable parts, and these are also the variable parts, while these are the constant parts. Okay, since this is a constant as well as this is also another constant, therefore this combination of these two is yet another constant which is written as Z. So Z means mu 0 a into small a, mu 0 b into small b, plus dot 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 plus minus mu 0 p into small p, mu 0 q into small q, and so on. Okay. Now from this left hand side part, the RT is common. So RT can be taken as common, and the logarithmic parts can be merged with each other. Here the plus signs can be merged as multiplication signs, while this minus sign can be represented as the division sign. That means a division. Here is the division sign, and here are the multiplication signs. So simple, RT is taken as common, and then ln in the numerator you are getting p into AP, and this coefficient p goes to the power of AP. Okay, that means actually it was p ln AP, so that small letter p has gone to the power of AP. Similarly, AQ to the power Q, AR to the power R. Okay, and in the denominator the same thing for the reactants. That means activity of A to the power number of moles of A. Look here, 3 A's are here, 2 small letter a and 1 capital letter A. Capital letter A denotes the species. Okay, this is the symbol of the species. Now this A denotes the activity of this species. So small a suffixed capital A means activity of the species, which is written symbolized as A. Now what about this A? This A is the number of moles of species A. Okay, so these 3 A's are completely different. Okay, so do not get confused. Okay, so A to the power A means the activity of A to the power number of moles of A multiplied by activity of B to the power number of moles of B, and so on. This is actually equal to Z, which is a constant. Now RT goes to the right hand side and it takes the position in the denominator, while Z is placed in the numerator. So we get Z by RT, and if this logarithm, natural log, is eliminated, then right hand side goes to the exponential power, so it becomes e to the power Z by RT. So as it is said that the whole operation is taking place at constant temperature, then T is also a constant. We know that R is gas constant, which is a constant, and Z is also a constant. That means exponential Z by RT is also another constant, and let us say this constant is Ka. Okay, and this Ka is the thermodynamic equilibrium constant of the chemical reaction. Okay, and you must have to mention somewhere that A, small letter a, represents activity. That is not concentration, that is activity. Okay, so this is activity equilibrium constant. You will have so many equilibrium constant terms. If it is written Ka, that means you have to represent this K in terms of activity. Okay, now let us move on to the same expression for the gaseous substances. Okay, now gases are generally real gases, and in case of real gases, activity can be replaced by the term fugacity, and similarly the chemical equilibrium Ka can be written as Kf. That means fugacity chemical equilibrium. Okay, so this is actually fugacity of P to the power number of moles of P, fugacity of Q to the power number of moles of Q. That means it was here A to the power A, I'm sorry, AP to the power P, here AQ to the power Q. That means activity of Q to the power Q, activity of R to the power R, activity of A to the power A. Here in this equation, when Ka is substituted by the term Kf, then A are also replaced, the activity terms are also replaced by the term fugacity, and you know what is fugacity. In the lecture series of application of thermodynamics, in the preliminary lectures, you have got idea about fugacity. What was fugacity? Now, fugacity is the idealized pressure of real gas. Okay, so this is equilibrium constant in terms of fugacity. Okay, so we have got two expressions, Ka and Kf. Now these are for real solutions and real gases. So when the concentration is multiplied by activity coefficient, then the activity terms are obtained. Or when pressure is multiplied by activity coefficient gamma, then fugacity is obtained. Okay, so we have to take into account the term activity coefficient gamma into those expressions of Ka and Kf. The concentration of the components can be expressed as C moles per liter, or in the mole fraction X. X has no dimension or unit because it's a ratio simply. Or if the components of the gases are gaseous, then partial pressure P can be used. That means, what is meant by this line? What is the explanation of this line? That means instead of fugacity, you can use the term pressure in atmosphere unit. Okay, but you have to involve the term activity coefficient also, otherwise you cannot do that. So all the above three concentration or partial pressure terms would accompany activity coefficient gamma in order to be equated with the activity or fugacity terms. How? Look, gamma are different types of gamma. If it is gamma C, then it is activity coefficient for molarity. Okay, if it is gamma X, then it is activity coefficient for mole fraction, and if it is gamma P, then it is activity coefficient for atmospheric pressure. And definitely gamma is dimensionless because it is the ratio and it is always less than 1. It's a fraction, isn't it? And look here, you will get the expression of gamma. Here gamma C is A by C, that means activity by concentration. Okay, this ratio is gamma C. Activity by mole fraction, this ratio is gamma X, while fugacity by pressure is gamma P. So it is clear now. Now we have the expressions Ka and Kf. In the expression of Ka, it is expressed in terms of activities. Okay, and in case of Kf, the expression of Ka is expressed in terms of fugacity F. So we can easily input these values into those equations. So from those two equations, we are now going to get three equations, isn't it? From the Ka expression of Ka, we are going to have Kc and Kx, and from the expression of Kf, we are going to have Kp. Is it clear? Okay. So here is the way how you have obtained these expressions. Okay. So Ka in terms of C and gamma can be written by this expression. Okay. Actually, it was activity of P to the power P, but since activity is C into gamma, okay, so it is activity concentration of P to the power P and activity coefficient of P to the power P also. Actually, Cp into gamma P whole to the power small p. So these two parts are separated. So concentration parts are separated here and the gamma parts are separated here. Okay, and here gamma is actually gamma C. This is second time mentioned for our convenience. Similarly, if Ka is mole fractional, then instead of A we can write X into gamma. So it is X gamma whole to the power number of moles of the component. If it is P, then it is Xp into gamma P whole to the power small p. So the Xp to the power P and gamma P to the power P parts are separated. Then this expression is looking like this. Okay, and here we have to mention that gamma is actually gamma X. Okay, and similarly the expression of Kf can be expanded like this. That means instead of fugacity of P to the power P, we are writing here partial pressure of P into activity coefficient of P whole to the power small p, and these two parts are separated, and this way we are getting here the P parts and here the gamma parts. That means here the partial pressure parts and here the activity coefficient in terms of pressure parts. Okay, so we have to get 3 more expressions, isn't it? Now the fact is that at very low pressure or at very low concentration, that means high dilution, gamma is almost equal to 1, and this part would be reduced to 1. That means they would vanish. Similarly, the same thing happens in this equation and these equations also. This equation is applicable for low pressure and these two at low concentrations. Okay, these two are applicable for solutions, so we have to say low concentration, and this is applicable for gases, so we have to say at low pressure. And in that case, Kf becomes Kp, Ka becomes almost equal to Kx, and this Ka becomes almost equal to Kc. Okay, so these are the extreme cases. So real solutions at high dilution or real gases at high temperature and low pressure behave almost ideally, and hence gamma becomes equal to 1. Gamma tends to 1. This gamma may be gamma C or gamma X or gamma P. Okay, so here this gamma is actually gamma C, gamma X and gamma P, and here Ka becomes almost equal to Kc or Kx, and Kf becomes almost equal to Kp. Okay, so we have got expressions of Kc, Kx and Kp. So we have got 5 expressions: Ka, Kf, Kc, Kx and Kp. Okay, so that's all for this lecture. Thank you. Have a nice day.